Kirchoff's voltage law, which is the second law of Kirchhoff's. So this Kirchhoff's voltage law, it is sometimes known as KVL in short, or loop rule. When I say loop, it means it is a closed path. A loop is a closed path. So in this law, we shall deal about a circuit which is a closed circuit. And first let us see what is the statement of this law. This law says that the algebraic sums of the products of the the currents and the resistances across any resistors, it is always equals to the algebraic sums of the EMF in the closed circuit. Alright, okay, suppose we are considering this is the circuit, right, and this circuit is closed. Right, now suppose this is a point A, this is a point B, this is a point C, point D, like this. Now in this circuit we have two external resistances, R1 and R2. These two external resistances are connected to a cell of EMF E and internal resistance small r. Let us imagine that the current which is sending by this EMF E, let's say it is I. So this current I will be flowing through R1 and R2 and as well as to the internal resistance R. So looking at this law, right, it says that the algebraic sum of the product, I will just write IR is equals to the algebraic sum of EMF. Now in this closed loop, okay, how many product of IR do we have? So in this circuit we have three products of IR. The first is IR1, because this current I, it is passing through R1, so the first product is IR1. The second is IR2, and the third is I small r. And the algebraic sums of all these products of resistance and current, it should be equals to the algebraic sums of EMF. But in this circuit we have just one EMF, that is E, so this is equals to E. Or I can say here that the sum of the product of current and resistance is equals to the algebraic sums of EMF E. Alright, okay. So please note down this law, it is actually based on the law of conservation of energy. Why? Because here we are talking about the potential difference. The product IR, it's nothing, it is actually the potential difference across the resistance. So that potential difference across the resistances like R1, R2 and small r, they are actually the work done, which is used to carry the charge from high potential to lower potential. So because this potential difference is a work done, similarly EMF also is a work done. So what does it mean? It means that this law here, it is based, right, on the conservations of energy, which means the energy which is sending by the cell to the circuit, right, so that energy will be utilized by the resistances in the different arms of the circuit. So all the energy consumed, right, by these external resistances as well as by the internal resistances will be equals to the energy which is supplied by the source of current. So it means the energy consumed, it is equals to the energy produced. So hence we say that the law here, it is conservative. I mean the energy is conserved. Okay, so please remember this point, that this law is based on the principle of conservation of energy. Okay, further, the to understand, because as I told you, this Kirchhoff's laws, it is actually used to to solve the complicated circuit, like to find out the current in the circuit, as well as, right, sometimes they may ask you to find out the EMF. But before that, before solving any types of question regarding this applications of these laws, you need to know about the sign convention which has been used in this case. So looking at this circuit diagram, we have two cells E1 and E2. Okay, now this cell E1, it is producing a current I1, and the cell E2 is producing a current I2. Now these two current, they are meeting at a point B, right? I1 is meeting at a point B, I2 is meeting at a point B. So therefore the current which will be flowing through the arm BE, it will be the sum of these two current, that is I1 plus I2. This is according to the first law of Kirchhoff's, that means Kirchhoff's current law. So hence I can say current, suppose if the current flowing through the arm BE, let's say it is I, so then I will be equals to I1 plus I2. Okay, all right. Okay, now from Kirchhoff's second law, when you do the when you solve the numerical problems, again you have to apply the sign convention. And the sign convention in this case, right, it can be easily understood by looking at this simple circuit where we have an external resistance and a cell along with the internal resistance R. Now this cell of EMF E, it is producing a current I, and this current I, it is flowing through the external resistance in this way. Okay, so now because Kirchhoff's voltage law, actually it is a loop rule, which means it is a rule, right, which actually applicable for any type of closed circuit. So this circuit that we are considering here, it should be a closed circuit or a closed loop. So if you consider the loop like A, B, C, D, A, right, if you consider this loop, so in this loop A, B, C, D, A, right, along this branch AB, right, the directions of traveling across the resistance, it is from A to B, which mean along the directions of current. So if the directions where you are traveling across the resistance is the same as the directions of current, so in that case the product IR will be positive. Okay, similarly after that, right, after AB we have BC, but in the arm BC there is no resistance, so that means there will be no potential drop. And now we comes to next arm, that is CD. So in the arm CD also we see the directions of current, right, it is in this direction, and the part you are traveling across this resistance, it is CD, which is along the same as the directions of current, so the potential drop across this small r also will be positive. Okay, however, if you are traveling across the resistance opposite to the directions of current, for example, if you are considering the loop BADCB, that means in anti-clockwise direction, BADCB. If you consider this, now across the arm BA, the product IR will be negative because opposite to the directions of current. Similarly, DC, along DC, the product IR will be negative because we are going across the resistance opposite to the directions of current. Now, what about EMF? Whether it will be positive or negative, so that we will see here. Now, in the first case, when you consider loop A, B, C, D, so right, the EMF is present in this branch. So now the directions, right, where you are going through the EMF, it is from negative to positive, negative terminal to positive terminal. So in this case the EMF will be positive. But if the directions of traverse across the EMF, let's say it is from positive to negative, like if you consider the loop BADC, so along DC, right? We have this EMF, and now since you are going from D to C, it means you are going from positive to negative terminal of the cell. So in this case, the EMF of the cell will be negative. Okay, so these are the sign conventions which are very important while solving the numerical problems regarding the circuit, when a circuit problem. Alright, so when you apply this law, so please take care about this sign convention, otherwise your answer will not come out. Okay.